Hello and welcome to ESMARConf2022 and Special Session 5, Other Quantitative Synthesis. As always, this session is being live streamed to YouTube and the individual presentations have been pre-recorded and published there as well. Subtitles have been verified and can be auto-translated for those individual talks. Automatic subtitles will be available shortly for this live stream. If you have any questions for our presenters, you can ask them via the presenter's individual tweet from the ES Hackathon Twitter account. See them on our feed. Presenters may have time after their talks to answer some of these questions, or at the end of the session if time allows. We'll endeavour to answer all questions soon after the event. We'd like to draw your attention to our code of conduct, which is available on the ESMARConf website at esmarconf.github.io. And I have the pleasure of now introducing Yves Plessen from VU Amsterdam.
Hello and welcome to my talk, What If? A very short primer on conducting multiverse meta-analyses in R. A multiverse meta-analysis is nothing more than conducting all possible meta-analyses for a given research question. What that exactly means will be covered later. Firstly, we will look at why one would even want to go through the hassle of conducting all possible meta-analyses. So why one would want to conduct a multiverse meta-analysis. Then we will talk about the basic idea behind multiverse meta-analyses and all the plots and all the analyses you can see here are prepared on my GitHub repository, so you can calculate and plot everything you see here. And then I will show you plots, a lot of plots. So now let's have a talk about the motivation behind conducting a multiverse meta-analysis. Imagine a scenario where there are multiple meta-analyses on the same research question, but with diverging results. We have meta-analysis A that actually does not find an effect on the research question of interest. Meta-analysis B is inconclusive, and meta-analysis C actually finds an effect. So you might suspect different reasons for these diverging results. For example, the individual meta-analyses might have used different methods: fixed effect, random effects, multi-level modeling. So this might be the reason for those diverging results. Or they might have used different criteria for removing outliers. They did not remove any outliers, or they used a specific cutoff, a fuzzy cutoff, and so on. Or they might have used different inclusion criteria. And the list can go on and on and on. But it is really important to understand why those different diverging results emerged. And this can be very tedious and also frustrating. This is where multiverse meta-analyses come into play, because they are perfectly suited if you have the same research question but different summary results. The basic idea and origin of multiverse meta-analyses began with this paper, Which Data to Meta-Analyze and How, by Martin Voracek and colleagues. The question you should ask yourself when conducting a multiverse meta-analysis is actually the title of the paper. You have to think about which data, which subsets of studies are eligible for your multiverse meta-analysis, and also how you could analyze those. So all the different meta-analytical models that could be used and are reasonable should be defined beforehand. If you want to dive deeper into this topic, I can recommend all of those 3 papers where you get the background that is needed to fully grasp multiverse meta-analyses. So, which meta-analysis or meta-analyses should I compute? Multiverse meta-analysis would suggest why not all of them. So the multiverse of meta-analyses for a given research question the multiverse meta-analysis, is basically the combination of A, all possible study subsets, and B, all available statistical and meta-analytical methods. Let me break this down for you a little further. First, we have to decide on the which factors, that is, which data or study subsets should we analyze. Imagine we have a research question: how effective are psychological interventions for individuals with depressive symptoms? Here we could decide to include studies based on different age groups, different sexes, or different therapies. And this could lead to different paths. For example, we could include only adults and only male participants and only studies that investigated therapy B. And you can also see that there are a lot of different resulting study subsets that could be analyzed. In our simulated example, there are 36 subsets of studies that could be analyzed in such a way. Secondly, we have to decide on the how factors, that is, which statistical and meta-analytical methods could we use to analyze our data. And here again, we could have three different factors that are interesting to us. The first one, how we handle effect size dependency. So when we have multiple effect sizes per study, what are we going to do with this? Are we going to keep all of those effect sizes, or are we going to keep only one effect size per study based on some criterion, or are we going to average those effect sizes? Those can all be valid methods, but lead to different paths that could be taken. We could also handle outliers in a different way. We could either remove them or we could keep them. And then there are different meta-analytical methods that we could use. For example, we could, when we kept all effect sizes, we could use a 3-level model or robust variance estimation. If we only kept one effect size per study, we could use p-uniform selection models. Or if we averaged our effect size, we could use a random effects model. And there are many, many more, but in our example, we have 36 different methods that could be used. And in total, when we multiply our which factors with our how factors, we have a lot of potential meta-analyses that could be run. And now, of course, it is important, what are we going to do when we have so much information and so many meta-analyses? Then we have to visualize them. And to do this, we can either use descriptive specification curve plots or inferential specification curve plots. Let's have a closer look. Here you can see our descriptive specification curve plot with simulated data. Let me walk you through this in more detail. We have our upper panel with the descriptive specification curve and our lower panel with the which and how factor combinations. Each of those vertical lines represents the confidence interval of a single meta-analysis. Down here on the x-axis, you can see that in total we have 160 meta-analyses included just in this one graph, in this one picture. On the y-axis, you can see our summary effect size, in this case hedges G, and this black line represents the effect size estimates ordered by magnitude from our smallest effect size to our largest effect size. Those colors represent the amount of included primary studies. Warmer colors include more studies, and cooler colors include less studies. You can also see a black dotted line representing the null effect, so all the confidence intervals that cross this line are statistically not significant, and a red dotted line representing our smallest effect size of interest. And now you can investigate why meta-analysis A and B and C diverged. We can have a closer look at the which and how factor combinations that are the reason or could be the reason for different results. Our meta-analysis A included all age group, only male participants, and all therapy types. They did not remove any outliers, and they used p-uniform to analyze the data and estimate the effect. And meta-analysis C, they made some different choices. They took different paths, but maybe even more importantly than pinpointing why single studies diverge is we can look at the overall picture from a bird's eye perspective and actually identify patterns. So for instance, we can see that female participants produced much larger effect size estimates than male participants. Therapy B produced much smaller effect size estimates than therapy A or therapy C. We can also see that removing outliers leads to smaller effect size estimates. And overall, we can have a very nice look at the robustness and overall evidence based on our which and how factor combinations. And here you can see the same plot, but simulated under a null effect. So all those confidence intervals actually cross the null line. So those studies or those meta-analyses would not be statistically significant and report quite small effect sizes. But here you have some outliers that are quite large in comparison. So it can be helpful to look at the descriptive specification curve to see how the overall evidence looks. Here is an example from an ongoing research project where we actually plot over 5,000 meta-analyses in a single plot to answer questions that are relevant for psychotherapy research. So it becomes quite overwhelming, but this plot helps us a lot in finding patterns and understanding how robust our evidence actually is. Here you can see an inferential specification curve plot with simulated data. And I simulated a real effect, so you can see that our red descriptive specification curve plot is different from a null scenario, which is represented by this gray line. To accomplish this gray line, I simulated data under a null effect and did some bootstrapping to get the 95% confidence intervals. And this plot is not in this area, so we could be pretty sure that the effect is different from a null effect. But in this example, I simulated a null effect. So here we already know that there's no true effect. And in this case, the descriptive specification curve is in our gray area. I highly recommend pre-registering or publishing a protocol for your multiverse meta-analysis, because it is quite funny that when you want to look at flexibility in data analysis, you can also fall victim to flexibility in data analysis. So it is a good idea to be very clear upfront what you are going to investigate and how you plan to do so. Here you can see some readings that I suggest. You already saw those two papers, but Julia Rohrer wrote a very nice blog post on dangers and pitfalls of multiverse analysis in general, and I can recommend this a lot. Thank you so much for your attention. If you are interested in the slides, you can find them at my Open Science Framework profile. If you're interested in the code for all the plots you have seen, you can find it on my GitHub repository. And if you are interested more generally in related topics, follow me on Twitter, where I post on a regular basis. Thank you. Bye.
Okay, and thank you, Yves, for that. And just a reminder, if you do have any questions, feel free to post them on Twitter underneath our the post relating to this session, and we will get them answered as soon as we can. Next up, we've got Megha Joshi from the University of Texas at Austin.
Hi all, thanks very much for watching this presentation and for attending this conference. I'm Megha, and I work as a quantitative researcher at the American Institutes for Research, and I'll be presenting on my package wildmeta, which implements cluster-wide bootstrapping for meta-analysis. This package is co-authored with my advisor, James Pasievsky. And we also have a wild hex logo designed by my talented friend, Raz. And the package provides functions to handle dependent effect sizes and meta-analysis. Typical meta-analytic techniques like meta-regression involves the assumption that effect sizes are independent. However, in social science and education research, it's common for each primary study to yield more than one effect size, or for studies to be nested in some way, creating dependence. For example, Tanner, Smith, and Lipsey 2015 is a meta-analysis examining the effects of brief alcohol interventions. The meta-analysis consisted of 185 studies, and in those studies, 1,446 effect sizes. The meta-analysis included primary studies which had multiple correlated outcome measures. For example, the alcohol consumption outcome was measured by frequency of consumption, quantity consumed, and blood alcohol concentration. The studies also included repeated measures of the outcome and multiple comparison groups, creating sort of correlated data structure, correlated effects data structure. There are several ways to handle dependence. One is to ignore dependence, but doing so can result in incorrect standard errors and incorrect inferences from hypothesis tests. Some ad hoc methods include selecting one effect size randomly per study or analyzing subsets of data separately. However, such methods result in loss of information. The ideal way to handle dependence is to use multivariate models, but to do so, it requires information on covariance or correlations between effect sizes, which are really hard to obtain from information provided in primary studies. Hedges, Tipton, and Johnson 2010 introduced another method called robust variance estimation, RVE, which doesn't require the knowledge of correlations between effect sizes, but uses sandwich estimators to estimate the variance. However, studies have shown that RVE only works well when the number of studies is large. Hedges, Tipton, and Johnson 2010 suggested over 40 studies are needed. And Tipton 2015 also showed that the performance of RVE also depends on the characteristics of the design matrix. Meta-analysis in social science research, however, typically have smaller number of studies. Over half of them have less than 40 studies. And when there are small number of studies, using RVE results in type 1 error inflation. And therefore, meta-analysts can conclude that some effect is present when it is actually not present. Tipton 2015 and Tipton and Pasievsky 2015 examined several small sample corrections for single coefficient tests and for multiple contrast hypothesis tests. And both recommended a method called HTZ test, which is CR2 correction for RVE, plus Satterway's degrees of freedom, an extension of that for multiple contrast hypothesis tests. The HTZ test was shown to control type 1 error rates adequately, but it may possibly have low power, especially for multiple contrast hypothesis tests. In my dissertation, I examined an alternative method called cluster-wide bootstrapping, which has been studied in the econometrics literature, but not in the meta-analytic framework. General bootstrapping is used to estimate unknown quantities by resampling many times from the original data. And cluster-wide bootstrapping involves resampling residuals by multiplying them by cluster level random weights. This is the algorithm for cluster-wide bootstrapping. First, we fit a null model and a full model on the original data. The full model consists of all the variables of interest in the meta-regression model. And the null model consists of variables except for the ones being tested in single coefficient test or multiple contrast hypothesis test. We obtain residuals from the null model, and then we generate an auxiliary random variable and multiply the residuals by the random variable, which is said to be constant within clusters. We can also multiply the residuals by CR2 matrices before multiplying by the weights. We then obtain the new outcome scores by adding the transform residuals to the predicted values from the null model fit on the original data. We re-estimate the full model with the new calculated outcome scores and obtain the test statistic. And we repeat steps 3 to 5 for R times, which is the number of Bootstrap replications. And we calculate the p-value as the proportion of Bootstrap test statistics that were greater than the original test statistic. In my dissertation, I ran 2 massive simulations to compare the cluster-wide bootstrapping test against the HTZ test. And I found that the cluster-wide bootstrapping test maintained type 1 error rates adequately and provided huge gains in power than the HTZ test, especially for multiple contrast hypothesis tests. Dependent effect sizes are common in meta-analysis in social sciences. If we use the original RVE as suggested by Hedges, Tipton, and Johnson, it can lead to type 1 error inflation, meaning high false discovery rate. If we use the HTZ test recommended by Tipton and Tipton-Dostoevsky 2015, it may result in low power, especially when you're doing multiple contrast hypothesis tests, which means that we may miss effects that are present. So we recommend the use of cluster-wide bootstrapping test, which balances type 1 error rates and also provides more power than existing small sample corrections. So cluster-wide bootstrapping algorithm is implemented in our package wildmeta. The main function of the package is called wildtest CWB. And the function works with meta-regression models fit using the Ruby function from the Ruby meta package and the RMA-MV function from the metaphor package. And these are the arguments required for the function. The full model is the meta-regression model fit using Ruby or RMA-MV with all the variables of interest. The constraints are like the contrast to be tested. R is the number of Bootstrap replications that you want to run. And we recommend a high number like 1,999 or higher, or like higher bootstrapping replications will result in higher power. For the rest of the arguments, you can please read our documentation online. This is the example data that I'll be using to show the functions of wildmeta. It's called SAT coaching and it's available in Club Sandwich package. It is a meta-analytic data studying the effect of SAT coaching on verbal and math SAT scores. It contains the study type variable, which indicates whether groups were matched, non-equivalent, or randomized, the hours of coaching done, and the type of test, verbal or math. It also contains the effect size and the variance associated with the effect size. And it is, as you can note, like one study can have multiple effect sizes because they have multiple outcome measures, correlated outcome measures. So there's a correlated effects dependent structure. This is the Ruby meta model. I'm running a model with zero-intercept, the study type variable, the hours, and the test variable, and running a correlated effects model using Ruby from Ruby meta. And this is the result from the Ruby model. So these 3 coefficients are the average effect for each study type, controlling for hours and the test type. And for multiple contrast hypothesis test, I want to study whether the effect of coaching differs based on study type, whether it's the same for matched, non-equivalent, randomized, or if it's different. To run the multiple contrast hypothesis test to examine whether treatment effects differ by study type, I'm using the wildtest CWB function from wildmeta. I input the Ruby model. I use the constraint equal function from the Club Sandwich package to create a constraint matrix, setting the first 3 coefficients equal to each other. I use 999 bootstrap replications and I set a seed. And this is the result that we get. we get the p-value from cluster bootstrapping, and if it's greater than 0.5, for example, if your nominal alpha is 0.5, you can conclude that there's no statistically significant difference in the effects of the SAT coaching across the 3 different study types. You also get information on what test you ran, any adjustment that you use, and the CR corrections and statistics used to conduct the WALT test. And here I'm fitting the same model, but using metaphor or RMA-MB function. I'm estimating a multi-level meta-analysis model with study type nested within study using RMA-MB. And the WALT test CWB works the same way. The inputs are very similar, and you get the p-value for the metaphor model. We also have a function called plot in wildmeta, which plots the Bootstrap distribution, Bootstrap test statistics distribution. So these are the F statistics from each of the Bootstrap applications. And this dash sign indicates the original F statistics from the original model. And the proportion of F statistics, Bootstrap F statistics that are greater than the original F statistic is the p-value for cluster bootstrapping. Thank you very much again for listening to this presentation. We have a website for this package, which has instructions on how to download the package from CRAN, please download, or from GitHub. And it has examples on how to use the package with the Ruby models and RMA-MB models. We have documentation on the functions and what all the arguments are. And we also have a vignette detailing what cluster-wide bootstrapping is and how to use it with Ruby meta models and metaphor models. Thank you very much. If you have any questions, please let me know.
Excellent, and thank you very much for that, Megha. So the next talk is from Alex Nicol-Harper from Southampton University.
Thank you. Is that showing correctly?
Yes, it is.
Great, thank you. So thank you very much for tuning in. I will be talking about how we have used sub-meta-analyses to maintain independence among spatiotemporally replicated demographic datasets. This is work that's done with Professor Patrick Doncaster and Professor Thomas Ezard at the University of Southampton, and Dr. Kevin Wood and Dr. Jeff Hilton at the Wildfowl and Wetlands Trust. So I'm just going to kick off with some acknowledgements. This is part of my PhD, which is through the NERC Spitfire doctoral training program. The lovely photo of Amanida that you can see on the slides is by Kate Evans on behalf of the Wildfowl and Wetlands Trust. And of course, a big thank you to my supervisory team. So a little bit of preamble, I'd like to point out that our meta-analysis is perhaps unusual in that we are considering mean values rather than a form of effect size. So this could perhaps be termed an informal meta-analysis in the sense of Morrissey and colleagues, since we are reporting on a distribution of values, which I mean specifically, but we are using meta-analytical statistical methods, in which case it's perhaps formal meta-analysis in those terms. And then another bit of preamble is the method that we're using. So it's an established method from Doncaster and Spake 2018, and it's inverse variance with adjustment for small samples. And what that means is that we can account for estimates that have a small sample size. That's the weighting accounts for that. And also it means we can include studies which don't have a associated variance. A more conservative analysis could exclude those, but sort of pragmatically we needed to include them to make the best use of our data set. So what we're doing with a random effects error structure, the meta estimate is the sum of the weightings multiplied by the estimates divided by the sum of the weightings. For the study level means, as weighted by 1 over bi plus t squared, where t squared is Cochrane's estimator, the Hedges and Holkin method specifically, and the study level error variance is vi, take the mean across the variances of all the studies divided by each sample size. So to reiterate, that's the it's that mean, which is allowing us to use mean variances rather than having one per study. And then we can include estimates. We can't include estimates without sample size, they're excluded because each sample size needs to be accounted for. And then the meta-variance is 1 over the sum of the weightings. So to get into it properly, meta-analysis is a useful tool in demography, which is the study of the components of populations. So an example meta-analysis is that for the spotted owl of Boyce and colleagues, where they say the meta-analysis can be used to combine results from multiple demographic studies replicated in time and space to obtain estimates of vital rates. In their case, they're looking at juvenile survival, adult survival, and fertility. And another example is the black bear study by Plessen. And here the plot shows cub survival values. And they also found that survival and fertility values varied across Eastern and Western North America. So that meant that while they couldn't perhaps use meta-analysis to derive continent level values, the process has uncovered new routes for analysis looking into the reasons behind that variation. However, demographic datasets tend to be messier than those which are typically subjected to meta-analysis. This is for 2 reasons. So firstly, because ecological datasets in general encompass a lot of natural variation and the presence of covariates with a large range of scale of replication. And then demographic datasets in particular tend to include lots of observational rather than experimental data, which might therefore be less sort of structured. Hence, demographic meta-analyses need to have careful application of accepted meta-analysis methodologies, for example, in relation to avoiding non-independence, which is what we're considering here. So we use population modelling to investigate breeding ecology and inform conservation for the common eider, which is this sea duck you can see here, which is a species of the circumpolar northern hemisphere. And our theoretical models are designed to be relevant for the species as a whole, and hence we wanted to parameterize them with some kind of global mean values of vital rates, similar to the demographic meta-analysis that I showed earlier. So we have a data paper which describes our collation of these vital rate estimates, and we had over 20 independent estimates for adult annual survival, clutch size, which is the number of eggs laid, and hatching success, which is the proportion of eggs producing young. And so for these, we wanted to do some form of meta-analysis where we had enough studies. However, we had a lot of internal replication. What I mean by this is where the researchers are going out into the field to gather data, often they're trying to answer a particular question. So for example, how does predator control affect adult survival? Does clutch size vary with age? Or how is hatching success affected by the presence of a predator such as mink? And this means they're out there collecting data across multiple years and or locations. So for example, adult survival across 3 colonies, as shown here in this example by Wood et al. Clutch size on different islands, for example, Egg and Stump Island in this case, but it might also be different types of islands, so open or wooded, or hatching success across multiple years in this case. So overall, we had this sort of internal replication for 7% of adult survival studies, 33% of clutch size studies, and 12% of hatching success studies. While these are themselves non-trivial values, it also shows that any type of full data analysis might have had a sort of intractable number of studies. So we need to be making best use of what we have. So how to make use of as much available information as possible while maintaining equivalence, so avoiding non-independence. So ideally, a meta-analysis involves single effect size estimates derived for each study in order to maintain statistical independence and avoid pseudo-replication. And so what we thought is that we could apply our overarching meta-analysis methodology to those cases where we had multiple estimates, but for one study. And I'll point out this isn't the same use of the term sub-meta-analysis as in Zuckman et al. 2015, but it aligns with the suggestions of Megha and colleagues in terms of adjusting sample size, variance, and weighting to represent true information content, or Hadaway and colleagues in that it's preferable to meta-analyze a reduced data set than vote count larger. So to sort of go through what we actually did, I'll take the example of that Wood et al. Study that I mentioned with the adult survival of different colonies, and this is one that fed into our study. So this is the data that you had. You have a different estimate with associated standard errors and sample sizes for 3 different locations within the study. So you go through essentially the same methodological steps as you would in the main meta-analysis. So you convert the standard errors to variances. You use those to calculate that mean variance, which then calculates the VIs, mean variance divided by the sample sizes, t squared, hence the weightings, And from there, you can calculate your meta-estimate and your meta-variance. Then when you're sending those through to your overarching meta-analysis, the estimate is just the meta-estimate, but the variance that you send forward is the meta-variance multiplied by the number of contributing estimates. So here there's 3, because there's 3 studies. And that allows compatibility with the calculated variance from the other non-sub-meta-analyzed studies. So to show how this affected our meta-analysis for adult survival, we've coded the sub-meta-analyses with the asterisks, and I'll highlight them here. So in the case of Cruz et al. 2012, the sub-meta-analysis across 2 replicates gives 0.72 as shown. You would actually get the same mean if you did just take a simple mean of the values. However, if you were trying to send one single estimate forward, if you'd chosen the most precise, so with the smallest standard error, that would have been 0.761, which is significantly larger. Similarly, with the Wood et al. Study, sub-meta-analysis gives 0.918 as shown. The mean across 3 replicants is similar at 0.916. However, if you'd taken the estimate, which was either the most precise or the largest sample size, that would be 0.94. So again, quite significantly larger. So the sub-meta-analysis is hopefully balancing information content against risk of bias. So with the Wood et al. Example, again, we have these 3 adult survival estimates across the 3 sites. As I said, if we selected the estimate with the largest sample size, that would likely overestimate. If we sent all 3 estimates through to the main meta-analysis, that would be lending false equivalence with the estimates from other studies, which are themselves usually means across areas or years. And so taking a mean, whether unweighted or weighted, as in this case with the sub-meta-analysis, reduces the risk of bias and ensures fair comparison. And this seems to be similar to Senior et al.'s second-order meta-analysis, but is theoretically close to the solutions to non-independence, which are offered by Megha and colleagues. So to do that comparison of the second-order meta-analysis, that's referring to essentially meta-analyses of previously published meta-analyses. And ours is similar in that it's 2 levels of meta-analysis. We're doing 3 meta-analyses, 1 for each vital rate, or varying numbers of studies, of which some provide a single estimate, which is itself a mean, and others provide the multiple estimates on which we are conducting the sub-meta-analysis to get the mean. So to show a sensitivity analysis for adult survival, if we just took a mean with all the estimates analysed equivalently, we would have 0.856. If we took a mean with the sub-means taken across those studies that we've discussed where we sub-meta-analysed, you'd get 0.857. If you do a weighted mean, where you're sending forward the most precise single estimate from relevant studies, you get something quite a lot higher at 0.861, whereas a weighted mean, either with simple means or weighted means for the sub-studies, gives 0.857. And while these numbers are not that different in the grand scheme of things, we're talking about survival, which is a probability, so ranging from 0 to 1. And it's a very important one for the species in the life cycle. And so actually small differences will make a big difference to the population growth rate, for example. I'll point out we did explore meta-regression, but there were no obvious relationships. So we were studying clutch size, which had lots of estimates. We expected it might vary geographically. There was no obvious pattern for clutch size with latitude, as we might expect, but there was a hint of reduced clutch size within the Arctic Circle. We wondered whether latitude was too simplistic. There are very different climate regimes across similar latitudes. So for example, 57 degrees north in Scotland versus Hudson Bay, you have an average January temperature of 3 degrees versus something like minus 25 with, completely frozen. And so that's really different, and perhaps we could estimate that or represent that through continentality and oceanity indices. So the former represents the cooling effect of land masses, the latter the warming effect of oceans. We found both of these to be marginally significant predictors of clutch size. So on the left, clutch size decreases with increasing continentality, so harsher winters, shorter breeding seasons. On the right, you can see that there's a hint that perhaps oceanity has an effect within the Arctic Circle, but not below, although that interaction is actually not statistically significant. So this sort of thing can be used for extension, but we had reason to focus on the single estimates for our modelling. So to summarise, our sub-meta-analysis addressed non-independence within studies to help us get our global mean vital rate, where there's evidence that where there is more interest in underlying drivers, or you have evidence of strong heterogeneity, such as between subspecies, which we didn't find here. Multi-level modelling would be the ultimate obvious method, as recently developed by Megha and colleagues. However, the associated code with that study implies that it would require a more balanced data set than ours, because we have studies providing single estimates across a single site year, single estimates where they've performed some kind of mean across multiple site year combinations, and those providing multiple estimates where we've conducted the sub-meta-analysis. I'll also point out again the messiness of demographic data. Some have no sample size and so were rejected due to our method. Some had sample size but no variance and are included with the mean applying to all, and a few provide both. Thank you very much for listening. I hope I've spoken to the importance of tailoring meta-analysis methodologies to non-standard situations, and hopefully it's accessible to ecologists and those sorts of users as well as meta-analysis specialists. And I'll just put the references up there. Thank you very much.
Brilliant. Thanks very much, Alex. So just a reminder, if you do have questions, please feel free to post them on Twitter or as a comment on the YouTube live video. I'm going to hand over now to Maria Llambrich from the University of Rovira and Virgili for our last talk.
Okay, hello, can you see my screen?
Yes.
Perfect. So good afternoon, and my name is Maria Llambrich from University of Rovira and Virgili, and I will present here Amanida, and a meta-analysis using overall results. First, I start with a brief introduction. So meta-analysis is a combination of the results in a single estimate and is used in clinical applications mostly, but we need a lot of academic findings to obtain the final clinical application. These academic findings can come from different files, and one file that is emerging nowadays is metabolomics. Metabolomics is the study of endogenous and exogenous metabolites in biological systems. These are small chemical compounds, and the aim is to provide information about all these chemical compounds in a system. By the diversity and the possible combination that exist, the number of chemical compounds is really high. For example, in humans, to date, we have identified more than 200,000 compounds, and this number is increasing day by day. A common workflow in metabolomics studies is you start with a sample, and then through high throughput technologies like mass spectrometry or nuclear magnetic resonance, you obtain a list of compounds that are present on that sample, the compound name and the intensity of this compound. And then you can perform the statistics on this list. Usually these are case control studies, so you have a disease like cancer, then you compare with a healthy control group. And you do two estimates. First, you compare the populations by the statistical significance to know the difference between these two populations, and also you calculate the fold change, which is the ratio, how change these two populations. But there are not standardized methods to report the results, so in each study the results reported may differ. When you want to do a traditional meta-analysis, first, you need some statistics that are present in all the studies. The most common are the mean, the standard deviation, and the number of participants. What happens in metabolomics is that the standard deviation or the error is not present in the study. So the number of studies that presents the error is a very few. So this don't allow you to perform a complete meta-analysis of all the studies from the same question. The other option will be make the meta-analysis with the raw data, but the size of the analysis using the raw data is very huge, and this is not feasible with the metabolomics information. For that, we developed an approach that uses these two single estimates, the p-value and the fold change, to perform the meta-analysis. When you cannot perform a meta-analysis with all the estimates, this is an approach to use this data and may have an information. The p-values are combined using a weighted Fisher method, and the weights comes from the study size. So it's not the same in a study with 100 participants than a study with 20 participants, for example. Then the fold change is combined logarithmically. This reduces the skewness that can come from the different techniques and methodologies to extract the compounds, and it's then averaged and weighted for the sample size. All this implementation of the meta-analysis is implemented in a CRAN package called Amanida. This includes the data import from common text files, the meta-analysis using the Amanida approach, also another qualitative analysis that is about counting that I will explain in a few moments, and visualization of the results, and also the data that you upload. So first, to use the Amanida, you can import your data of the component. We are talking about metabolomics.
Maria, yeah. I'm really sorry. You cut out for about 5 seconds there, so I don't know if you can just go back and repeat what you said.
Yeah, from here or?
Yeah, so you managed to introduce the package and then it sort of cut out a little bit when you talked about what it included.
Okay, so this is the CRAN package, Amanida implemented. And this includes the upload of the data from simple text files. Then you can perform the Amanida meta-analysis approach. It also includes a qualitative estimate that is about counting. I will explain in a moment deeper. And then visualizations of the plots of the results and also the data that you upload. So Amanida starts with the upload of your data from a simple text file. Here we're talking about metabolomics, about chemical compounds. So the idea in this case are the compound name, and then you need the p-value, the fold change, the sample size, and if you want, you can include the reference where this data comes from. Then with the function compute Amanida, you obtain the meta-analysis results, so the p-value combination, the fold change combination, and the sum of the sample size. In case of metabolomics, another disadvantage is that not all the studies disclose the same compounds. So the sample size will differ from one study to other and from one compound to others in the total results of the meta-analysis. Talking about chemical results, you can complement the results of the Amanida meta-analysis with information about the chemical compound, like the molecular mass or the molecular weight, and also public IDs from databases of these compounds. Then you can visualize the results in a classical volcano plot. Volcano plot plots the logarithmical fold change versus the logarithmical p-value. So significant results will be the ones that are in top right and top left. And here you can see by the dashed line the values that are over the cutoff established. Biology, usually fold change over 2 is considered significant. It means that have some effect in the body. Then in some cases, the fold change is not disclosed numerically. So we only have the trend of the change. We know that a compound is upregulated or downregulated. In this case, the options for meta-analysis are less. So the only option is to do a qualitative estimate. This is the vote counting. So we assign a vote for each trend. A compound that is upregulated will have a +1, and a compound downregulated will have a -1. And then you compute the sum of all these votes. As before, you can complete all the information about the qualitative analysis by the public databases information, and also visualize the results. Here you can see a bar plot with the total sum of the votes for each compound present in the literature. What happened is that we realized when we were doing a meta-analysis with urinary compounds for colorectal cancer that in some studies the trends were not consistent. For example, we can see here that citric acid was found upregulated in 2 studies, but in other 3 studies was found unregulated. But by the different sample size of the studies, the total combination of the p-value was significant. So for this, we developed the explorer plot. In this case, when we have a significant result, we can confirm if this significant result is consistent across all the literature in a first glance. All these functions are also implemented in a Shiny app for non-R users with the same functions that we have explained. So you can upload your data, a text file, then you choose if you want the quantitative or qualitative analysis, depending on the data that you have, and select the columns to do this analysis. In case of some rows have missing data, this won't be used to perform the meta-analysis, the Amanida or the bot counting either. Then you go to the quantitative analysis and see the results. By the volcano plot first, when you can choose the p-value cutoff, and also you can choose the cutoff for the fold change. Then in blue, you have the significant compounds that are non-regulated, and in red, the significant compounds that are upregulated with the p-values that you have selected, and the same table that you obtain when using the R package. If you move to the qualitative analysis, you find the plots for the votes and also the explorer plot to confirm your results. All these functions and results can be downloaded in a report. This is an HTML file where you have all the information with the tables and also the plots. You obtain the results for the Amanida, the approach, and the vote counting also. So thanks to all to hearing me, and thanks to my supervisors and collaborators that have worked with me. If you have any questions, I will try to answer it.
Brilliant. Thanks very much, Maria. That was great from everybody. We haven't had any questions yet via YouTube or Twitter, so just encouraging those who are watching to please feel free to submit their questions. We do have a few minutes left, so I wanted to ask, I guess, if anyone who's here had any questions for any of the other presenters on any of their presentations. Got some stunned silence there. Excellent. So I thought they would all the presentations were excellent. So thank you so much for giving up your time to talk about your work. It was really really fascinating seeing sort of the developments that are happening in this field. If we don't have any questions for each other, and we haven't had any questions from Twitter or YouTube yet, I think we can let you all go a few minutes early. Thank you just once again for all of your contributions today. It's been really, really interesting.
Thank you for